Okay, cool. We've been recorded now. It's my pleasure to have Pavlos Motakis here to speak about L1 of LP being primary. Please, Pavlos, you have the floor. Go for it.
All right, thank you very much. Thanks for the invitation. So as the title of the lecture suggests, I'm here to talk to you about the proof of the fact that the Banach space L1 of LP is primary. So primariness is a very classical property of Banach spaces. It is very easy to define, and I will do that shortly. It just uses the notion of projections and isomorphisms inside Banach spaces. And I'm very excited to be able to share with you this result about this very classical property being satisfied about this very classical space of functions defined on the unit square with a double integral norm. So although this property is very, very simple and elegant and easy to define. And so the result we proved is very easy to state. The proof contains many different tools, and I would not be able to effectively communicate to you all the details. So instead, what I intend to do is talk a little bit about the background, the history of the problem, how it emerged, what has been known about many classical spaces. Then I want to talk to you about the methods that have been used to prove that Banach spaces are primary, and how recent insight has allowed us to simplify some of these old methods to obtain known results, and then how these observations that we've made relatively recently helped us to achieve this this recent result. And the shame on me, I forget actually to say, it's written of course, but I should have said it out loud, that this is joint work with Richard Lechner and Paul Müller, both of whom are at Linz in Austria, and Thomas Schlumprecht from Texas A&M University. Okay, so let's start with the background. So what is a primary space? What notions do we need? What spaces are known to be primary? So it has to do with projections. So we're in a Banach space, an arbitrary Banach space. And the bounded linear map is a projection if its square equals the map itself. And the image of a projection is called the complemented subspace of the ambient space X. And the notation that we will use is this hook with a C on top. So Y is complemented in X if it is the image of a projection in X. And whenever we have a projection, an elementary remark is that the identity operator minus said projection is a projection as well. And if we call Z, I'm having trouble saying Z now because I moved to Canada recently. I'm more inclined to say Z. So if Z is the image of the complementary projection, so P is the projection identity minus P is the complementary projection, then we write that X is the direct sum of Y plus Z. So this means that there is a projection P, so that Y is the image of P and Z is a C, and Z is the image of I minus P. And a very famous, at least within Banach space theory, a very famous result that involves these notions of complemented subspaces is due to Pelczynski from the 1960s, or at least it appeared in 1960, it might be even earlier, when it was proved that if you go to one of the classical sequence spaces, so little C0 or the little LP spaces, in the separable range, then any complemented subspaces, as long as it's infinite dimensional, it has to be isomorphic to the whole space. And in order to prove this, he had this very elegant method that is nowadays called the Pelczynski decomposition method, or although I think it appeared slightly earlier. It's his method, but he used it even before this paper. So a little bit later, oh, sorry, I skipped the slide. So very important. So a Banach space with this property, with the property that every infinite dimensional complemented subspace is isomorphic to the whole space, is called the prime space. And it was slightly later proved by Lindenstrauss that the space little L infinity is prime. So at this stage, what was known is that all classical sequence spaces, so C0 and the little LP spaces, either separable or non-separable, are prime spaces. All the complemented subspaces that are infinite dimensional are isomorphic to the ambient space. However, being prime, it's a very uncommon property actually. Beyond these classical spaces, there are very weird, complicated examples that are known to be prime, not natural at all in any sense. So it is not, it's not a very common property, and there is, at least in the classical setting, there is not much to study about it. You have to go to a non-classical setting. So there is another definition that I will get to. Yes, of course. And okay, here's an example of some spaces that are not prime. So once you escape from the classical spaces C0 and the little LP, and you go to their function versions, so namely the continuous functions in 0, 1, or the measurable function spaces, then they contain complemented subspaces that are isomorphic to corresponding sequence spaces. So they're not isomorphic to the whole space. So these spaces are not prime. But they satisfy something else, something nice. And what Lindenstrauss and Polchinski proved in 1971, in particular about the space of continuous functions, so this is where they started, they proved that if you take it and you decompose it into two pieces, right, so they are both images of projections, complementary projections, then one of the two pieces, either Y or Z, has to be isomorphic to the whole space X. And the definition that was introduced slightly later, not yet in this paper, is that the Banach space with this property that whenever you decompose it, one of the two pieces has to be isomorphic to the whole space. This is going to be called the primary space. And using this opportunity, using this result of Lindenstrauss and Polchinski, Lindenstrauss initiated a very influential program in 1971. So he wrote a paper in which he only asked questions. He didn't prove anything. So he wrote a paper that he published in which he only posed questions with regards to complemented subspaces or Banach spaces. And basically what he asks, this is not exactly how he asks it. I will tell you how he asks it, and then you will agree with me that it is more or less equivalent to this. So he said, basically, determine what Banach space is X. So find the Banach spaces X that they cannot be decomposed into two pieces, Y and Z, so that both Y and Z are infinite dimensional. So you want a true decomposition. You don't want to get rid of finitely many dimensions. You just want to have a true decomposition into infinite dimensional pieces. And so that both of the pieces are not isomorphic to the space X. So for what spaces can I break it up into two pieces, neither of which is isomorphic to the whole space? And so this is not exactly how he asked it. And now I will tell you how he asked it. He basically had a few questions, and here are two of those questions. The first one was find indecomposable Banach spaces. And these are the spaces, by definition, that don't have decompositions that satisfy A. You can never decompose them into two infinite dimensional pieces. And as weird as this might sound as a property, such spaces exist. Back then, they were not known to exist. They were first discovered in the 1990s. And one of those examples, very famous in Banach space theory, is called the Gauss-Maurey space that solved the unconditional basis sequence problem in Banach space theory. And another such example is a famous space in Banach space theory, the Argyros-Hayden space, which was the first space on which every operator is a compact perturbation of a scalar multiple of the identity. So they are such weird spaces. So this is the one question, and the other one question you might be guessing already is determine the primary spaces. And the primary spaces are exactly those, all of whose decompositions fail B. So whenever you manage to break it up into two pieces, at least one of them has to be isomorphic to the whole space. And then posing problem one, posing problem two, you should agree with me that this is more or less asking the same question. So a remark that is worth making is that classical spaces are always decomposable. You really have to find very exotic examples for them to be indecomposable. For example, if you look at function spaces, classical ways, or let's say standard ways of decomposing them, is by taking restrictions and conditional expectations and things like that. So these maps define projections with infinite dimensional image and infinite dimensional complement. So because of this, there was actually a second part to his problem. So this is how his problem was actually asked. First, this sentence, then second sentence. In particular, he would like us to determine the separable classical primary spaces, because in the classical setting, there aren't indecomposable spaces. They're always decomposable. So I want to look at problem 2 for classical spaces. And this program was hugely influential. So it started in the 70s, and for many decades, there have been results about primary spaces in the dozens. Many classical spaces have been proved to be primary. And what I want to do next is present to you some of these spaces that are known to be primary. So I will start with what are the main classical spaces. What a classical space is up to interpretation. I don't think there is a strict definition that says this space is primary, is classical, and this space isn't. But these are the spaces that Lindenstrauss himself called main classical spaces in his paper where he asked the questions. So it is C01, the space of continuous functions on a unit interval, where Lindenstrauss and Pelczynski proved, I mentioned earlier, that this space is primary. Then you can look at C of K spaces for K countable compact sets. And this was proved to be primary by Billard in 75 and independently by Alspach and Benjamin slightly later. And these two together bundled up, if you use Milutin's theorem, they cover all separable C of K spaces. Then slightly later, Enflo and Maurey proved that capital LP for P in the separable range, so we're not looking at L infinity, is a primary space. And a comment to be made here is that this was actually a method developed by Enflo, and the paper is written by Maurey. They did not write the paper together. It was only written by Maurey, but Maurey attributes it to Enflo, and he writes it with Enflo's permission. This is how it is stated. And slightly later, Alspach with Enflo and Odell again wrote the proof that capital P, where P is strictly bigger than 1, is a primary space. And of course, this result is covered by the previous one. But the difference is that what they actually observed is that if you go in this range, in the range in which LP is reflexive, then the proof is simpler. It simplifies. The proof above uses some additional tools that are not required here if you're in this range. And it is also worth mentioning that later came a paper of Enflo and Starbird, which proves L1. And this is a completely different method to the previous two papers. This is a much deeper paper. And it has a very, very deep and involved study of all bounded linear operators on capital L1. And it is more related to the question, what are the complemented subspaces of capital L1 in general, which is still open actually, after many decades. But as a side effect, as a byproduct of the proof, they also can extract with a completely different approach that capital 1 is primary. So there are many more. Let me just mention a few, just a few. For example, Bourgain proved in 1983 that H infinity, which is the space of bounded analytic functions on a unit disk, is a primary space. Dranowski and Roberts proved under the continuum hypothesis, interestingly, that the quotient L infinity over C0 is a primary space. And what they actually proved under the continuum hypothesis is that this space satisfies a certain decomposition property, which helped them prove that it is primary. And it is an interesting remark to make that much later, so fairly recently in 2014, Christina Brech and Piotr Kosmider, they proved under the negation of continuum hypothesis and some additional set theoretic assumptions that L infinity quotient C0 does not satisfy these certain decomposition properties. So therefore, it is still unknown in ZFC whether this quotient is primary or not, or whether this is independent. And since we're in the operator theory seminar, operator algebra seminar, the bounded operators on a Hilbert space have been proved to be primary. And in related spaces, projective tensor product of LP with LP and some other cases were proved to be similar spaces, projective and injective tensor products were proved to be primary by Arias and Farmer.
Right.
Yes.
For the L infinity mod C0, is it expected that it's independent of ZFC?
You know, I'm not an expert in this. I just found it very intriguing that this proof is until now it's unknown whether it is dependent or independent. So what they actually proved is that only a certain part of this proof actually fails under the other axioms. So it's not unknown, it fails. And so therefore, if you would like to prove it in ZFC, you would have to do a different route, like a completely different route. You cannot copy the proof of Dranowski and Roberts. So I don't have any intuition, to be honest with you. Okay. Because this decomposition property that they used is very standard way of proving that things are primary. So Brechen and Kosmider killed the standard approach. So I don't know. I don't know. Okay. But it's very interesting, very interesting.
All right, thanks.
Okay, so there are many others. I'm not going to talk about others, but there are many others that are known to be primary. And of course, many that are unknown to be primary. But I want to talk about some that are particularly relevant to the lecture. So they are the Bochner-Lebesgue classical spaces. And just to give you an example, not a general definition, but the example of a Bochner-Lebesgue space is capital P of capital Q. And one way of understanding this object is by looking at all functions defined on the unit square with values in R or C, doesn't matter. Anything I'm talking about today works in either R or C, where this double integral norm is satisfied. So these are functions on the unit square where on vertical lines, they look like LQ, and in horizontal lines, they look like LP in a very specific way. So in Capon, in 1982, Michel Capon proved that LP of LQ in the reflexive range is primary. And this is a very deep proof, but it uses certain facts that were not available to us in the result that we proved. Although this looks very similar to what we proved, our proof here, the P is equal to 1, and her proof misses P equals to 1. And there are some properties there that if you are P between 1 and not equal to 1, they fail miserably. So we could not use this tool. So our proof has absolutely nothing to do with that proof, I dare say. And then slightly later, in a paper that is perhaps even deeper and uses even more tools, she proved that capital P of X, where X is a subsymmetric spaces, the subsymmetric basis is a primary space. And if you don't know what the symmetric basis is, I think I said subsymmetric, doesn't matter. If you don't know what the symmetric basis is, just imagine a little LQ space in the separable range. So it's something like above where you don't have functions defined on the unit square, but on the unit interval, and their values are sequences, they're not scalars. So this is a very deep proof, and at this point in time, when we're talking about Bochner-Lebesgue spaces, the ones for which primariness was still open was whenever there is a 1 inside. I'm forgetting L infinity. I'm not putting L infinity because this makes things non-separable. So I don't want to make things messy with non-separable. So L1 of LP for P between 1 and infinity, and LP of L1 for P between 1 and infinity. So these are at this point the unknown Bochner-Lebesgue spaces. So this type of spaces, at this point, the ones that are unknown. And so what we actually proved is this here. We proved that this is primary, and I will speak to this in just a moment. But a comment I want to make is that actually the proof for us was not a direct path. We did not arrive here right away. What we first did is we proved this result of Capon. We never published this, but we wrote for ourselves a proof of this result that was substantially different to Capon's method. And then we were able to extract from our approach a proof for this result. Okay, so let me just state our theorem. So if you take any P except infinity, then this Banach space, capital L1 of capital P, this Bochner-Lebesgue classical space is primary space. And just a comment that I would like to make, that we prove something slightly more general. We don't need to take capital P. We have something that a wider class of spaces. In particular, if you take any rearrangement invariant function space over the unit interval. So these are function spaces that are, when you take a function, you take any other function with the same distribution, then this has the same norm. For example, here such space. And you want some assumptions to be satisfied. I don't want to get into these things. And then you have to actually not look at the whole space, but the closure of the simple functions, the closed linear span of the simple functions. Then L1 of this Y would be primary. And for example, if you look at reflexive Orlich spaces, which are in some sense classical spaces, if you look at the reflexive case, if you take the nicer ones, then L1 of the Orlich space is going to be primary. These and others are covered. Okay, so this is with regard what I had to say with regards to the history of the problem. What I want to talk about now is methods of proof of primariness. So mostly I want to make a reduction. Before saying the word reduction, I want to make a connection, is the right thing to say, to the study of bounded linear operators and factorizing operators. So this is a crucial component of this approach, both in the classical setting of capital P spaces and in the Bochner-Lebesgue setting of LP of LQ spaces. Secondly, So after I make this connection, I want to make a point about what I mean when I say reduction of operators, not reduction to operators, but reduction of operators. This is an important part of this proof as well. So I want to explain exactly what I mean. It's taking operators and reducing them, reducing the operators to simpler operators in order to be able to get to the problem in successive, to the solution of a problem in successive steps. And after this, after I've talked about this general approach, I want to tell you how these translate to the classical setting of capital LP spaces, not biparameter spaces on the unit square, but on the unit interval, just a simple setting. And then at the end, we'll go back to our theorem. Okay, so here's the definition. Of course, you're probably very well aware of these definitions. So I have a Banach space X, fixed Banach space X, and I have two operators, T and S. And then I say that T is a factor of S if I can write S as a product of three operators where T sits in the middle. So S has these three factors, B, T, A, and T is one of them. And of course, it is important here to demand that both A and B are defined on the space X and not on some other space. Otherwise, this would not be the same. This is an important distinction. And there's a very strong connection between factors and complemented subspaces, because there is a very simple result that states that if you have an operator T that is a factor of the identity. So what this means is that I can write the identity as BTA, where B and A are some bounded linear operators. Then I can find inside the image of T a complemented subspace inside the image of T that is isomorphic to the whole space X. So there exists this very significant and yet simple connection between bounded linear operators, factors of bounded linear operators, and the study of complemented subspaces. And the proof here, there's no need really to go through it. I just want to make a point that the proof of this proposition just comes down to verifying that this operator is an isomorphism from X to X tilde, and this operator is a projection from X to X tilde. So there's nothing really to this. This is a very simple statement. So a corollary that can be made, and this has been used many times to prove that some Banach spaces are primary, is that if you have a Banach space X and it satisfies two properties, the first one is that it is isomorphic to the LP sum of itself. So this means you take X, you take infinitely many copies of it, and you connect them with an outside LP sum. So if X is isomorphic to its LP sum for some P, P could be anything, doesn't matter, for some P, or maybe even this is zero sum, still works. This is one property. And the second property you want X to satisfy is that any bounded linear operator defined on X, for any T you start with, then either the operator itself or the identity minus said operator is a factor of the identity. So either the identity can be written as ATB, I mean BTA, or the identity can be written as B identity minus T A. One of the two has to happen for every operator. So under these two assumptions, it follows that X is primary. And let me just give you a sketch of this proof to see this very important connection, why we study factors of operators with regards to primariness, which is this property about decomposing Banach spaces. So the proof is the following. You start with an operator with a decomposition X. So what does this mean? I have a decomposition. It means I have a projection onto Y, and then the complementary projection is onto Z. Then if I apply this property here, I have this property, I apply it to my operator P, so T is P, and then by the proposition in the previous page, okay, I have to arrive to the fact that since one of them is a factor of the identity, one of the images has to contain a complemented copy, which is isomorphic to the whole space. So if P is a factor of the identity, then the image of P contains a complemented copy of X. If I minus P is a factor of the identity, then Z, the image of I minus P, contains a complemented copy of Z. So now we assume, just for simplicity, assume that the first thing happens, so that Y contains a complemented subspace isomorphic to X. Now there exists this famous Pelczynski decomposition method, which I will not go through completely, but what it says is that if you have one, so if you have this property here, which is appropriately called the accordion property, because you can take X, stretch it out and stretch it back in, it's the same thing. That it says that if your X has this property and you take X, you take a complemented copy of X I mean, you take a complemented subspace Y in X, and then inside you can find another complemented copy, then the sandwich copy in between has to be isomorphic to the whole space. And this is an argument that is by no means obvious or trivial. It is a genius argument, but it is since the 1950s and 60s, it has been a standard argument. So let me just like draw maybe a picture here. So you have X, and then from X you can project to Y, you can project here, and then from here you can project to this. Let me zoom in just temporarily here. To this X tilde, which is isomorphic to X. If you have this image with projections going from one to the other, then the guy in between has to be isomorphic to X. So this is called Jensen's decomposition method. Okay, so there is this connection that we made. So it's very nice to know that we can connect primariness, this classical property, to studying factors of operators. Now there is another thing that I said, and I now want to explain, is what do I mean when I say reducing operators, not reducing two operators. I think now we reduced the problem to the study of operators, but I want to talk about reducing the operators themselves. So there's a slightly different notion, which I'm not aware of its existence. And maybe if it exists, you can let me know. But me and my co-authors and no Banach space people I talked to, that were familiar with this definition and being used explicitly as a tool. So the definition is the following. So I have two operators, T and S, defined on the Banach space X. And I say that T is a projectional factor of S. So this is going to be more than just being a factor. If I can write S as a product of three operators, where T sits in the middle. So S has these three factors, B, T, A, and T is the middle factor. But I additionally demand that the outside operators, B and A, they multiply out to the identity. So B is the left inverse of A. So I demand this additional condition. And you might ask, why are you calling this a projectional factor? The reason is the following, is that if you look at the image of X, of A, this is isomorphic to X. Okay. And if you look at AB, so BA is the identity, but AB from X to AX is a projection. So the image of A is the copy of X, and it's a copy in which you can project via this operator AB. And then you can write B, of course, as A inverse times AB. And this inverse is well defined because A is an embedding onto its image. So you can define its inverse, and AB is a projection to this image. So this is well defined. So what this basically captures is S captures the behavior of T on a complemented subspace of X, and it's also isomorphic to the whole space. Now let's see what this has to do with our problem, the problem of primariness, and why it has to do with reducing operators themselves. So here are some properties of factors and projectional factors. So the first one is that if I have three operators, T, S, and R, and T is a factor of S, and S is a factor on R, then T is a factor of R. So being a factor is a transitive property. And this is just, can be verified directly. Secondly, also by direct verification, if T is a projectional factor of S and S is a projectional factor of R, then T is a projectional factor of R. So you have these A, B's, and A, maybe A prime, B prime. And if you multiply them out correctly, then you just get the identity again. And this is also just a verification. But the fact that projectional factors satisfy and factors don't satisfy, so you need projectional factor for this, is that if we assume that T is a projectional factor of S, then the identity minus T is a projectional factor of the identity minus S. And this just comes down to the fact that this BA is the identity. So if you try to write this out, then just because the identity is B minus A, this works out like a treat. So the corollary we can deduce from this is the following. So I have an operator T0 defined on some Banach space. And wishfully, I would like to show, because I'm aiming to prove primariness for X or something, I want to show at the end, this is the conclusion I want to reach, that either T0 itself or the identity minus T0 is the identity, because we explained earlier that this has to do with primariness a lot. Okay, so the corollary says, if I start with a T0, and then I have a finite sequence of operators, T1 to Tn, And each guy in the sequence, starting with T0 all the way to the end, each guy is a projectional factor of the next guy. This is one thing I know. And the second thing I know is that only for the very last guy, Tn, or the identity minus Tn, I can only say it for the last guy, is a factor of the identity. Let's assume I can say these things. Then T0 or I minus T0 is a factor of the identity. And the proof, I don't want to write it down, but let me just say it out. This is very simple. So if we assume that Tn is a factor of the identity, okay, then because being a factor is a transitive property, then the identity is a factor of T0. Okay, because I pull this back step by step through all these operators which are factors of one another, at least in a forward way. If on the other hand, I minus Tn is a factor of the identity, then because I minus T, by transitivity of projectional factors, T0 is the projectional factor of Tn, then I minus T0 is a projectional factor of I minus Tn. So therefore I can say about I minus T0 that is a factor of the identity. So from this observation, I can say that we can truly reduce the problem. I start with an operator T0. I want to show for an arbitrary operator T0 that is a factor of the identity, or I minus that is a factor of the identity. If I use this process of passing the projectional factors, I'm allowed to reduce my operator to simpler operators. And if I can show it for the next guy, then I pull it back to the previous one. And sometimes this is what we do in our proof. There is this process with many steps where you pass the operators which are better and better and better and nicer. And we arrive at the end of an operator for which we can finally prove that either that or the identity minus that is a factor of the identity. And then we can pull it back to our original T0, which was completely arbitrary. So this is where I'm trying to get to. So this, I hope I convinced you that this is truly a reduction of operators. So we have a method of reducing our operators to simpler operators and be able to solve the problem there instead of at the initial one. Okay, so now I want to make the connection to first to how these tools translate. So tools were stated more or less like this, not exactly like this, because I didn't need all this projectional factor business in simpler examples. But I want to talk about how they translate to the classical setting. And in particular, I mentioned there are these papers in capital LP. One was Enflo Maurey and one was Alspach Enflo Maurey. And I want to talk about those and how what the modern approach is for capital L1, which 1 is the problematic case I mentioned at some point. When you are P equals 1, then some nice tools that work for P bigger than 1 just don't work. So I need to remind you some things about capital P spaces, but I'm sure you've some familiarity with them. So I want to remind you the Haar functions. So if you are in capital LP on the unit interval, for every dyadic interval I, so it is an interval of length 1 divided by 2 to the n for some n, and its endpoints are some I and I plus 1 divided by 2 to the n. Then on this interval, so here it is, this is a dyadic interval, I define the Haar function hi, which has the value 1 on the first half of this I and the value -1 on the second half. Now it is well known that in the separable range, at least, in this LP spaces, this system, the system of Haar functions with an appropriate enumeration and together with a constant function, they form a basis. So it's a Schauder basis with an appropriate enumeration. This means that everything inside your LP space can be written as a linear combination, an infinite series with scalar multiples of these Haar functions with an appropriate enumeration. And pertaining to this definition of this particular basis, there is the notion of a Haar multiplier. So if you're on a given P, then a function T, a bounded linear operator on initial P, is called the Haar multiplier if every function is an eigenvector of T. So it's a Haar multiplier. It's, I don't know, something like a normal operator, I suppose, on a Hilbert space that has an orthonormal basis of eigenvectors. I mean, not all of them do, but you know, one of those, like in finite dimensions, for example. But it's not with respect to an arbitrary basis. It's respect specifically with this basis here. And of course, this is not an orthonormal basis, but it's a type of basis. So there is a remark here that I would like to make is that when we escape p equals 1 and we are in this range here, then this Haar system as a basis, it has a property called unconditionality. And what this means is that if you have, whenever you have a convergent representation, whenever you have a convergent series that represents some element in your space, then by dropping coefficients in your series, this still converges. And this is a very strong property that fails for p equals 1. It fails blatantly. And what you can extract from this nice property is that Haar multipliers are completely understood what they are in the range between 1 and infinity, strictly between. So these are all the operators that have eigenvalues that could be anything that's a bounded collection of scalars. Any bounded collection of scalars indexed over the dyadic intervals defines a Haar multiplier in this range here. For p equals 1, this fails miserably. And something that one can extract for this is that, for example, a Haar multiplier is invertible if and only if its entries, its eigenvalues, are bounded away from 0. And this follows from this unconditionality property. And for p equals 1, this is no longer true. And this is now I want to talk about the Alspach Enflo Odell approach in the observation that the space LP, where p is strictly between 1 and infinity, is a primary space. They use this nice property of unconditionality of the Haar system. So here is a proposition that relates this to the language of projectional factors. So you start with an arbitrary bounded linear operator, t, from LP to LP. And then this is a projectional factor of a Haar multiplier, up to some small perturbation, which doesn't really affect the arguments. And I want to give a sketch of the proof. I don't want to get into it too much. I just want to convince you that this is a very canonical process. So the idea of the proof is that you use Rademacher sequences. So Rademacher sequences are independent 0, negative 1, negative 1 valued sequences. And in any LP space, except in infinity, these are weakly null sequences. So they behave very well with respect to the weak topology. So you can use them to annihilate things, make them very small. So what you basically do is you build a new Haar system, not the original one on the dyadic intervals, but you build a collection of functions which are distributionally equivalent to the original ones. So all together have jointly so the system has the same distribution as the original system. So therefore they behave exactly the same. But on this new system, your operator is almost like a Haar multiplier. So maybe the eigenvalues, maybe the Haar functions are not exactly eigenvalues, but up to small perturbations, they're eigenvalues. This is what this says. They are very close to being eigenvalues. They're approximate eigenvalues. And the idea of doing this is like you start inductively, you build these HI tilde, so your new system, you build it inductively. And whenever you have built finitely many pieces, then you know what your next guy needs to look like, in the sense what you want his support to be, in which set you want to define him, and you want it to be 1, negative 1 valued. So you take a Rademacher function of very high frequency, so this orthogonality is satisfied. So this is a very elementary process. If you ever worked in capital P spaces, you maybe had to do this yourselves. So this is why, for the purpose of the lecture, I'm calling it the canonical projectional factorization procedure. And the reason why I'm giving it this name, so it is very canonical, it's a very canonical process. You build a new Haar system. In the sense of distribution, it's the same as the original Haar system. And you make on this new system, your operator behave like a diagonal operator, like a Haar multiplier. And I'm calling it a projectional factorization procedure because there exists this subspace Y, namely the one spanned by this HI tildes, which is canonically isomorphic to LP. So you have this canonical isomorphism from LP to Y. And then there exists also a projection, which is a conditional expectation with respect to some appropriate signal algebra generated by those HI tildes, which goes from LP to Y. And then you can combine these to show that your T is a projectional factor of a Haar multiplier. And the projectional factor, what you do is you take this T and then you borrow its approximate eigenvalues in this new system with the H tildes, and you borrow them and you put them on an operator which is defined on the whole space LP, and it is an actual Haar multiplier with those eigenvalues. And then this is up to some small perturbation. You have that T is a projectional factor of that new operator. And so after they did that, they use the theorem, which is slightly older than their proof. It's in LP spaces, it's a very famous theorem. It's the Gamlen-Gaudet theorem, which said, it doesn't say exactly that. I will tell you what it says, but first let me read what I wrote. It says that any Haar multiplier from LP to LP, and importantly, P has to be in the range between 1 and infinity, which is the range in which this Haar system has this unconditionality property. Any multiplier, any Haar multiplier, their theorem says, is a factor, either the multiplier itself or the identity model of the multiplier is a factor of the identity. And what they actually wrote, they didn't write it like this. What they actually wrote is that if you take Haar multipliers which have values, eigenvalues only 0 and 1, this is how they wrote it, because they were looking at subspaces generated by the Haar basis, by subsequences of the Haar basis in capital P. But their proof goes through even if you don't assume that they're just 0 and 1 valued multipliers. If they're anything, then it still goes through. So then what Alspach, Enflo, and Odell did is neither of these two things are their ideas, neither this nor that, or Alspach and Odell's ideas. What they did is they put 2 and 2 together, and they realized that they combined these two things to show that LP is primary. Why is this the case? Because every operator is a projectional factor of a Haar multiplier. Every Haar multiplier is a factor of the identity, or the identity minus the multiplier is a factor of the identity. So you can pull this back to your original operator. And then by this Plotzinski decomposition property, your space LP is primary. And if you were very observant, then you might observe that something here lit up is that this proposition here works for P equals 1. This part of the proof even works for P equals 1. This is because Rade Mahar, weakly null, even capital 1. But this here, by no means does it work. The Gamlen-Gaudet theorem, at least in the way it is written here, does it work for Haar multipliers in capital 1. They critically needed unconditionality, critically needed it. So just a few comments about the other approach, the Enflo-Maurey approach, which includes both the P equals 1 case and the P finite case. What they proved is that if you start with any operator, an arbitrary operator, then what they proved is that this is a projectional factor of a multiplication operator. So there exists a G so that mg sends every f to g times f, pointwise product. And this here is, at least from some point of view, a stronger result from the previous with the Haar multipliers, because maybe you like and understand pointwise multiplier better. But this is this proof is definitely more involved than the previous one, where you just use the projectional, where you just use the canonical projectional factorization process. So this is a deeper result. But the comment is that this was deemed to be entirely necessary for the case P equals 1, because people back then had no clue about what to do with Haar multipliers in capital 1. So you have to do this extra work to extract, to reduce your problem to a pointwise multiplier instead of a Haar multiplier. And once you are the Haar multiplier in any LP space, then it is quite easy to show that either the multiplier itself, the pointwise multiplier, or the identity minus the pointwise multiplier, which is again a multiplier, is a factor of the identity. And you just find some set of positive measure where either G or 1 minus G has value at least a half or something like that, and then you factor through there pretty easily. So therefore L12 is primary with this argument. So what I want to talk about now is our approach in capital L1. So what we did differently in capital L1. So in order to talk about our approach in capital L1, what we did is we realized that there is a better understanding nowadays of Haar multipliers in capital L1. So let's see. Let's start with an arbitrary Haar multiplier, and let's in L1, and let's assume we know its eigenvalues. So it's these lambda i's. What I want to do is I want to represent the Haar system, which is defined over the dyadic intervals as a tree. And just looking at this picture here, the tree is pretty obvious. So here's a dyadic interval, here's another guy, and so on and so forth. And you can already see the tree structure. So the tree structure is this here. So you just draw down the tree. And based on this tree, we can look at branches. So a branch is just, a chain, a maximal chain inside this tree, and I can go and linearly order the intervals that are associated with this branch, I1, I2, I3, and so on. And this goes down to infinity, it never stops. Now, we can go and define a value S triple norm associated to this S, which does the following thing. It goes and looks at the branch, and then it looks at this quantity. And this is an L1 variation. Maybe you're familiar with L2 variation or one variation. That it's a sort of variational norm. And it does this for every branch, and then you look at the supremum. And what was proved remarkably recently is that this formula here for any Haar multiplier on capital 1 defines a quantity which is equivalent to the norm of the Haar multiplier, the operator norm. And this was not known until very recently. So this is truly remarkable that people did not know what to do with Haar multipliers on capital 1, and this was not considered or discovered before that. And with this theorem at hand, it is then a relatively easy corollary that every Haar multiplier on capital 1 is a projectional factor of a scalar operator, and a scalar operator is a scalar multiple of the identity. And I won't write down the proof, but I will tell you a few things of how it works. So by using this formula here, the formula of Semenov and Uksusov about the norm of Haar multipliers, what it basically tells you, this variation, if you have something that has bounded variation, basically means that the values are very rigid, they're very close to each other. There's not a lot of variation. So what this shows is that you can actually find a big fat triangle. So there is some point, so that if you start at that point, at one of the nodes of your tree, and then you look at everything under the tree, absolutely everything, no holes, no nothing, then if you restrict your operator here, all its eigenvalues have to be so much close to each other so that here it behaves like a scalar operator. So they're all the same. Not only they're epsilon close to each other, but they're so close to each other that in the operator norm, this is as close as you wish to a scalar operator. Okay. And once you have this in hand, which just follows by this formula and no fancy argumentation or nothing, it's just a blow up argument. If you assume this doesn't happen, then you have to deduce that this is infinite. This is all you do. So by this argument, I can see that my operator in this copy here of L1. So if you look inside the subtree, it defines a copy of capital L1, which is complemented. So this tells you that the scalar operator is a projectional factor. I mean, your S is a projectional factor of a scalar operator. So then, using this, one can deduce that that L1 is primary. And what is the process for this? You start with an arbitrary operator on L1. Then you use the canonical projectional factorization procedure to really reduce your problem to a Haar multiplier. So now you only want to show for your Haar multiplier that it's a factor of the identity, or I minus that is a factor of the identity. And then by the Semenov-Uksusov formula, you reduce your problem to a scalar operator. So you truly have a reduction. So you started from arbitrary, you reduce to multiplier, then you reduce to scalar operator. And then T is a projectional factor of a scalar operator and some small perturbations that you can account for. And then it is very easy to show that for any operator, either itself or the identity minus the scalar operator is a factor of the identity. Therefore, L1 is primary. And this is similar like our Alspach Enflo Odell approach. We put 2 and 2 together. We realized that two things work well together. And we didn't actually state it this way because we were proving something different, but we made this realization that we have this very good control of Haar multipliers in capital L1, and they help us actually make proofs easier instead of making proofs harder. So in the past, people didn't know how to work with Haar multipliers in capital L1, but actually it turns out that instead of being a disadvantage that the base of capital L1 is not a nice basis, the fact that it is not a nice basis, it means that Haar multipliers, if they are bounded, they have to be extremely rigid. Otherwise, they couldn't ever have been bounded. So this turns out to be an advantage. So how much time do I have?
You can keep talking for, let's say, another 5 minutes.
All right, so then I can just like blaze through the steps of our proof. So outline primariness of the space L1 of LP. So I made all this fuss about this talk, about this history, because our solution to this problem is intricately connected to studying operators on capital L1. This is why I wanted to make this connection. So let me just remind you. So this is the space we're looking at. So it's the space of all functions defined on the unit square that define this double integral formula where this is bounded. And this is a space. And since you're operator theory people, then maybe you prefer this identification. In fact, capital L1 of capital P can be identified with a projective tensor product of capital L1 with capital P. And being a projective tensor product, you can talk about tensors. And if you take an F in L1 and a G in LP, then of course in the projective tensor product there exists this element, but if you want to identify it with how it looks like in this representation of your space, this is just a function that whenever you look at it on point ST in the unit square, on S it sees F and on T it sees G, and then you take the product of that. So here's the strategy. The strategy is start with an arbitrary operator T from capital L1 of capital P to capital L1 of capital P. Then consecutively, starting from arbitrary, reduce to simpler operators step by step. And there are many steps. But at the final step, arrive at an operator S. So we will finally reduce to an operator S from L1 to LP of the following form. It is of the form R tensor I. So what does this mean? This means that R is an operator from L1 to L1, so that if you act your S on any simple tensor, then basically S just is R acting on F and it leaves this part alone. So this here is in L1 and this here is in LQ or LP. I wrote P, so let's keep the terminology standard. So it only touches the L1 part and it doesn't even mess at all with the LP part. And once you did this after a lot of work, then you recall, hey, you know, R is defined on L1, and on L1 I already proved that either R or the identity minus R is a factor of the identity on L1. And then by just a standard tensor argument, it follows that S or I minus S is a factor of the identity on L1 of LP. And therefore, L1 is primary. So, and this is of course because we reduced to this operator for which we could show that the identity or I is a factor, so that S is a factor of the identity or minus is a factor of the identity. And I swept this under the rug, but this space L1 of LP also satisfies this accordion property. It's isomorphic, it's L1. So just a few words of how we do this. So in order to talk about operators, we need to have some representation for them. And I want to talk about how an operator can be represented as a matrix of operators, all of which are defined on capital L1, because the ones on capital L1 are the ones that we finally understand so well. So one observation that one makes is that if you take any F in L1 of LP, then this can be represented as an infinite sum of tensors, where on each component on the right side, you have the basis, the Haar basis in LQ or LP, I keep saying Q. This lives in LP, and this here lives in L1. So the right side is fixed, it doesn't depend on F. So what I did is I took my F and I represented it. So F can be identified with a collection of functions in little L1. So it's a column, let's look at it as a column, a vector, whose components are all in capital L1. And because every component of L1 of LP has such a representation, I can, in a standard way, represent every operator on L1 of LP as a matrix of operators, each of whom is defined in capital L1. So this tells you how each component goes to what other component in what way. So you have this identification of T as a matrix of operators, and importantly, each of them is defined on capital L1 because we understand these operators. This is what we want. And now, given this representation, I will call an operator diagonal if in this matrix representation, its off-diagonal entries are all 0. So a diagonal operator in every meaning of this word. And in this case, we can just identify T instead of with the whole matrix. We can just identify it with its diagonal entries and call those Ti. And then how T acts on an F, it basically just takes its representation as a series, and then it just messes with each coordinate, and it doesn't do anything between coordinates. It doesn't swap between coordinates. It only messes everything inside its own coordinate. So it acts like a diagonal matrix, so to speak. So here's our first step. Our first step is we start with an arbitrary operator from L1 for P to L1 for P. So let's call it T0. It's our starting point. We show that this is a projectional factor of a diagonal operator, up to some small error we can account for. So the idea of the proof is the following. So the first thing that you do is you start with T0 and you write first a projectional factor. You write it as a projectional factor of the T1 tilde. So this is not a diagonal operator, but all the off-diagonal entries are Haar multipliers. And relatively speaking, this is not a very difficult step. You do it manually. You don't use that much theory. You just do it by hand. You just have to define the right operators that witness this projectional factorization. And this is sort of okay. And the next step is we have to use certain compactness properties or families of Haar multipliers to take these entries here that are all Haar multipliers and eliminate them. And here, to do this, we have to use these compactness properties, which is a new tool that we had to develop. So this is one of the tools we had to develop for this whole proof. So then we have at hand, we reduced our problem for an arbitrary operator to a diagonal operator. But so what we want to do is show that for this diagonal operator, either the identity factors through it. I mean, it is a factor of the identity, or the identity minus that is a factor of the identity. And this is not immediate. What we need to do in the next step is we want to show that T1 is a projectional factor of another operator, T2, so that this is also a diagonal, and its entries satisfy this very, very strong stability property. So they are all very close to each other. And this is the most important part of the proof. And basically what this says is, so you have your operator T2, and it has these Ti's, and these Ti's are indexed over the dyadic intervals, which are a tree. And then I take any Tj here, and then I look at everything under it, and I take any Ti in here. And then the distance of these two guys is some epsilon j that only depends on j. And epsilon j can be prescribed to be anything you want when you start your proof. And let me just tell you some idea about the steps. So the first thing you have to do, and this is the most involved part of the whole paper, is you have to use a concentration of measure argument to show that your T1, your x diagonal operator T1, your diagonal operator, reduces to another diagonal operator T2, so that its entries are uniformly eventually close to Haar multipliers. And not to get too technical, what this actually means is that you have this set of operators, and each of them, its tails get closer. So the tails of the operator, so you forget about the initial part of the space, they look more and more like Haar multipliers, and this happens in a uniform manner for your whole family here. So this is one thing that you have to do. Now then, because you have these things that are uniformly close to Haar multipliers, you use compactness properties again, these tools of Haar multipliers, to deduce that this T2 tilde can be reduced to a T2 hat, so that these entries of this operator, they are a relatively compact set. Not the operators are compact. This is an important thing to remark. The operators themselves are by no means compact. The set of operators in the operator topology, that the norm operator, the operator norm topology is a compact set. And then you repeat the concentration of measure argument to show that T2 hat reduces to a T2, where the entries, the set of entries from being very, very close, so they're compact, you make them very, very close in this very specific sense. And then once you have done this, once you have an operator T2 that satisfies this here, this very strong rigidity of its entries, then there is a final perturbation argument that says that I can show that this is very close to an operator, which is what I wanted, of the form R tensor identity. Because all the entries are very close, it has to look like something like this. And therefore, with these stepwise reductions, we show that T0 is a projectional factor of this S, which is of this form, and therefore L1 of LP is primary. And I will blatantly do this. I will just leave the question page open, and I will stop here. Thank you. And sorry for going beyond time.
No, don't worry. Thank you for the talk. Thanks for the nice talk.
Thanks.
And do you have any questions for Pavlos?
Yeah. So I'm operator algebras type person, so I'm going to always ask the same annoying question we always ask, which is, what if you make one of these spaces not commutative? Like, what if you take like a non-commutative LP space?
I don't have the faintest idea. I don't know. I try to follow some of the non-commutative business, but with regards to this problem, I haven't given it any thought at all. It is, of course, a very, very good question. So probably I should have looked into this before coming here. I should have looked at what happens to the non-commutative LP spaces. Are they primary? This might be known, but I don't know. Yeah, so this is the first thing to look at, I suppose.
Right, sure.
Yeah, like if you go to the Stratton class spaces or whatnot, are they? Probably.
Yeah, or even I think, the question could be interesting for like, non-commutative L spaces associated with things that are sort of like atomless like atomist non-commutative probability spaces.
Right. Yeah. I don't know. I really don't know, but I'm sure I'm 100% sure that people have looked into this, and at least in the classical examples, it should be known.
Sure.
It should be known, and I now realize my mistake of not looking into this before coming.
No, it's fine. It was just a
yeah. Yes, of course.
Do you have any other questions for Pavlos? So are you guys looking at the LP of L1 now?
Yeah, of course we are. Yes, we are. And
when is the paper coming?
As I think, I don't know if you were there last time when I said it, the paper is written, but the paper is being polished.
No, I meant of LP of L1.
Oh, this, we haven't got the proof.
Oh, actually, the question is in the slide right now, right?
One of LP is what we proved. And
no, the thing I'm asking is actually one of the questions now, right? Okay.
Yeah, so LP of L1, we are looking into it. We have no proof. There are certain things that just work the same way, and there are certain things that don't work the same way. And the question is, can they be overcome, or do you need a completely different approach? Yeah. Mm-hmm. Because one thing is that L1 of LP is a projective tensor product, LP of L1 is not a projective tensor product. So this is actually a problem. So how much of the projective tensor product do you really need?
Okay.
And the one that is more near to our approach is the one of C of K. So L1 of C01 or L1 of C of K, where we have some problems and it doesn't work, but there is some hope that you can overcome just a few things and make it work.
Oh, by the way, you mentioned in the beginning of your slides about C of K. What was it? If K is compact, if K is countable?
Yeah, if K is countable, then if K is countable, then K looks like a well-founded tree. So there is some hope there.
So, but is there a characterization of when C of K is primary regarding K, by the way?
Oh, for K metric, it's always primary. If you go to K non-metrizable, then there are some characterizations.
Okay.
Not complete characterizations but there are Benjamini and Alspach and Benjamini have a characterization for C of alpha, where alpha is an ordinal number.
Okay.
I don't know for any metric space, for any topological space. But in the metric space setting, it is always primary. In the topological space setting, it is not always. Yeah, and in some cases it is known. I don't think it's known in every case. I would be surprised.
Is it even known just for L infinity of 0,1 or something? I mean, that's a C of K, right?
Yeah, but L infinity, so there is a theorem of Pelczynski, probably one that made him famous, that capital L infinity of 0,1 is isomorphic to little infinity of bounded functions.
Sure.
So as a Banach space, you can't say much more there. So Lindenstrauss proved that the space is primary.
Okay, yeah.
But it becomes very interesting if you look at capital L infinity of something. If you go to a Bochner space, vector valued L infinity, then there is very little known actually. There are some cases in which it is known, not in print as far as I know, but it is known to us at least. Some cases they can be made to work, but I don't know if anybody ever wrote them down.
Okay, thanks. Is there any other question?
Maybe I can just briefly go through my second half of the question slide, since
Sounds good.
So this is actually like months ago when Braga asked me to give a lecture. I said I want to talk about this, and back then I told him if I prove something good, I will tell you, and I will talk about something else. And actually, this is exactly what I meant. I was hoping to be able to talk about what I talked today. I was working really hard on this. So I'm very happy. But what I actually had initially planned to talk about is about this property, which is called the factorization property. It's about the Banach space X with a basis. So you have a space X with a basis, a Schroeder basis, and then it's said to have the factorization property if the following thing happens. For any operator, so that its representation, its canonical representation as a matrix on this space with a basis, has diagonal entries bounded away from 0, then this must be a factor of the identity. So if on X, every operator with big entries on the diagonal is a factor of the identity, then we say that X together with this basis, it's a property of the basis in reality, has a factorization property. And this is a property that is very closely related to primariness because the methods of proof are interchangeably used in both topics. And let me say that we would have never proved this result if we hadn't studied the factorization property for a few years. So some spaces known to have this property are LP in the reflexive range P between 1 and infinity, proved by Andrew in 1979, LP of LQ for P and Q in the reflexive range, proved by Lausten, Lechner, and Müller recently. And capital 1, so this is a paper I mentioned earlier of me and my co-authors of the same work, where we observed these things about Haar multipliers on capital 1, where we used this to prove that L1 has a factorization property. But however, in our current work, although all these methods are interchangeable, there is some problem and we can't make the factorization property, we can't prove it. And it is not completely out of question, but it is open to us, and we would be very happy to know if we can like modify our proof to make this work, because studying the factorization property gives you a lot of intuition of how to work in primariness and vice versa. Right, so that's everything.
Thank you. Okay, well, thanks again. We'll stop the recording now.